Okay, normally, when you're awake early, something that's still asleep. That's still asleep up to this time. I actually have a class. This is the reason why I'm actually awake in the first place. It's not even like, oh, wait, alright, that's a big class. Yes, I have a class right now. I don't even know if people are actually watching this. Because, join the link. I'm sending the link to the group. The microphone's still on, so they can be hearing your whole conversation. Okay. Yeah. Oh, and I'm fine. How did you sleep? Okay, yeah, it's recording. So starting now. So as I said, today I'll be looking at real functions or real variables. So under real functions and real variables, normally what comes about and what you're actually talking about or looking at is basically functions. Let's say, for example, remember last time how we had that equation, the example I given you guys, how we had that equation, and then from there we now had to make the equation be in function of x, and then we had to now solve the equation, and then I remember x was equals to -1 if I'm not mistaken. And then from there we now wrote some domain function where um it was open bracket. Yeah, it was open bracket. Then the first bracket was a closed bracket, and then we had -1, then comma, positive infinity, then the bracket at the end was open. So we'll be looking at how to come about such things, how to solve them, what happens from this point here and from this point here. Yeah, that's basically what we're looking at today. Yeah, we want to look at how to solve different limits as well. Look at the different rules which are under real functions and real variables. Yeah, so basically that's our topic for today. Yeah, so we'll have to try to wrap it up because we're going to have analyze both from 8 to 10, and I'll come again from 15 to 17. So we can finish this topic today and probably even start another topic called development limited. So we'll start that as well later in the day, according to how fast we're going to be in understanding this topic. Yeah, it's very, very fast. It's very, very simple. It's a very understandable topic. And at least this topic, unlike suits, is more understandable in the sense that here you do a lot of solving. You actually see where things are coming from, why this is this and why that is that as well. Yes. I hope you guys can get me. I hope I'm very, very audible. Please let me know if I'm very, very audible. Yeah. Okay. Am I audible enough?
Yes, you are.
Okay, perfect. Perfect. So, okay. I'm sure. Okay, so I'm sure you guys all have this PDF. Yeah, you guys all have this PDF. This PDF is very, very detailed. I would advise you guys to try and sit down and really just read through and really try and understand what the PDF says. Okay, what the PDF says. But for today, what I'm going to do is I'm going to give you guys a summarized version of this topic, because here it's, but I'll still come back to it and still talk about it as well. Okay. Yeah. So first and foremost, looking at that. So the first thing I'm going to do is okay. I'm sure you guys are actually going to really enjoy this topic, because you guys are going to be involved in the topic. You're going to be involved in the solving and everything. And you guys even know that makes math much fun and more easy to understand than everything else. Let me just get my pen as well. Yeah. Okay. Where's my pen? Okay. Found my pen. Perfect. So I'm sure you guys can get me now. I'm using my phone right now, so I can solve for you guys. Let me just sorry. I'll do that there. Okay. Okay, I'm sure you guys can hear me now, eh? Yeah. Perfect. So, today we're going to be looking at. Give me a second.
Mono, your mic is on mute.
Oh, sorry. Okay. Sorry, I didn't see that. Okay. So today we'll be looking at real functions and real variables. So the first thing that we have to think of, what is a real function and what does it mean when they say a real function, and what is a real variable? So basically, under real functions and real variables, when you're asked, or like when they bring about, when you even see the word real functions and real variables, the first thing that should come to your head is that because it's real, that means that it's real. That means that we all know what real numbers are. So you now bring about the concept of real numbers. What are real numbers?
what are real numbers? Because real functions are a part of real numbers, and variables as well, and real variables are part of real numbers. Yeah. So whenever I look at real functions and real variables, there are two indications or two letters that we use. We're going to be using letters D and letters R. So what's going to happen? Letters D and letters R. So under real functions, we're going to be, by definition, by definition, we'll be looking at two letters. So we're going to say application. So we're going to say application. So say application, we're going to have D and we're going to have R. So we'll be looking at these two letters, D and R, in this sense. Yeah, D and R. D and R. DR, and actually the R, which represents real numbers. Yeah, so we're looking at these three letters here. So what's going to happen? Now what's going to happen is that we are now going to define real numbers in the way we normally define, like how we used to define under, suite, and everything else. So the first thing we're going to say is we're going to just say F. Yeah, we're going to say F, which means a function. Yeah, F, which means a function of where D is going to be a member of R, right? Of where D is going to be a member of R. Then now this same R is going to be a member of real numbers. That's the first thing. That's the first thing we note. The other thing that also exists whenever we're looking at real functions and real variables is we now have to have an X. There's always going to be an X. So also going to say this X, the X that we have is going to indicate F of X. As usual, we know that X always implies F of X because F is a function of X. That we already know there. Yeah. So by definition, this is the first part we're going to look at. An application of three letters, D, R, and the R for real numbers. And then we also introduce X. What is X? X normally is written under F of X because that there represents a function which has variables of X and everything else. Yeah. Yes, yeah. So this is the first part. And then this is the first part. And then the other thing now, how do we now like our notation under real variables? One thing that's there, the first thing that's there, we have df, and this df means domain function. So we are going to use this a lot. So this is this is 2, this is 1. So we have the application, and then we now have one of the symbols we're going to be using, which is d and a small f. D and a small f, which implies that x is a member of real numbers as usual, of where f of x exists. This is how we have defined this part here. Okay, this has been defined. Yeah. So as usual, we all know why this is like, we all know this whole thing because I'm sure we've been seeing this the previous times when you're looking at the suites and everything else here. Now we're going to look at our first example under real function. So the first example we've been given, example 1. So what we have here, we have f of x is equals to the square root of 1 minus x squared. Yeah, of where x is a member of real numbers. So now how are we going to find the domain function of this? Yeah, what's the first thing we do? So first of all, the first thing we're going to do is these are now the steps you have to take. The first thing you do is you're going to say x is a member of df. You see that, x is a member of df, and then you're going to put this equivalent sign like that there. Then you're going to get rid of this square root. This square root that's here is going to be gotten rid of. So you only keep what's inside. You have 1 minus x squared, which is greater or equals to 0. Yeah, is greater or equals to 0. The reason why we have introduced this is just for us it's basically just one of those things you introduce because it's the most simplest thing you can introduce. Normally you just introduce this sign so you can find your value of x, because you can't put less than, because this already here, whatever it is you put here probably has a high chance of it being greater or of it being greater than the value.
Why did you get rid of the square root?
No, it's just that way. Those are just the rules. You just have to get rid of the square root for you to solve the question.
Oh, okay. So is there anything else that we do apart from this thing while we get rid of the square root?
Oh, now I'm getting there. Now I'm getting there. Okay. Yeah. So the first thing we've done is this square root. We've gotten rid of the square root. Okay. The second thing we do is now this time around you have to make sure you keep this equivalent sign. This equivalent sign should be there. It should be there. Then now what's the next thing you're going to do is this one will come this side. This one will come this side. Yeah? So we're going to remain with negative x squared will be greater or equals to negative 1, isn't it? Like that, right? Yeah. And then normally what happens when you divide both sides by a negative number? What's going to happen? The sign will change, right? Yeah, the sign is going to change. Yes, yeah, the sign is going to change. Yeah, the sign is going to change. So the sign will change to have x squared is greater, because here we're going to divide both sides by negative 1 and everything else. Yes, yeah. Yeah, we'll divide both sides by negative 1. Then this sign will change. This sign will change to become this other side here. And then from there, we're going to have 1 like that there. The sign will hold on to the sign and everything else here and all that. Yeah. And then now from here, since we now have this is now what we now have at this point in time, right? What's the next thing that's going to happen? The next thing here that's going to happen is, since here we've seen that here our value here is x squared, right? Our value here is going to be x squared. Our value here is x squared, and there's a possibility of us having a negative 1 and a positive 1. And in this case here, this is just how it is. So what you do is the first thing we do is we have our negative 1. We say negative 1 like that there. It's going to be less or equals to x, right? Which would be less or equals to 1. You get that? You see that? So from after you've gotten rid of the square root, which we did there, you get what's inside the square root. You have 1 minus x squared. You have 1 minus x squared there. Then from there, you now introduce greater or equals to 0. You now find a value. Then you're now going to find a value of you now find the value of x, and we know that even if we square root this side, it will still give us x is greater or equals to 1. That's just how it is. And then from there, what do you do? From there, our x here is actually the main thing we're looking at. The main thing we're looking at in this case here, you have your x there, which you're looking at there, and then from there, you're going to now make some sort of function, or I don't know how you can call it, like a set, which is going to be negative 1 is greater or equals to x, which is greater or equals to positive 1. So you have that. This is an example how you would solve something like this. Then from there, what do you do? Now, what's our domain function from here? Our domain function is actually going to be
No.
yeah.
I've got a question.
Yes.
Like, how did we come up with the fact that x is greater than negative 1? Was that an assumption, or how did we get to that? Because from there, we just had to square root both sides and to give us positive 1 and negative 1. And how did we know that x is greater than negative 1?
Which part?
That part where we came up with a domain down there.
Here.
Yeah. Where we've got both negative 1. Yeah.
And positive 1. Okay.
Yeah, how did the sign change the direction?
How did the sign change the direction?
Yeah, on the negative part, because yeah,
On the
if we
negative.
root, yeah.
Okay. So what happens? Is that the sign that you have at the end of the day is a sign that you have to maintain throughout. The sign you have to maintain throughout whatever it is you're writing. You have to maintain the same sign, because here you cannot put because you can't keep the same sign, because what happens is this sign was there at the beginning of the equation, but then now what's your sign when you simplify everything? Once your final sign, and our final sign here was this sign here. This is why this sign is one that has been maintained throughout the entire equation that we have found at the end of the day. Yeah, this is why it's like this. Yeah.
So we just have to maintain the sign.
Yes, have to maintain the sign. Yeah. Yeah. And then after we have our negative one, after we have our negative one after we have our negative one and our x and our positive one. So you're going to get, you get the two numbers that you have, and those two numbers are now going, is what's going to now determine what your domain function is, which is how we've written it in negative one, comma, positive one. And in this case here, they are closed because of the sign that we have. Our starting point here is negative one, and our ending point here is positive one. This is why the brackets here are closed. This is our first example. This is why the brackets here are closed. Yes, yeah. So this is our first example. Our second example, we're going to have
Mono. So I've
yes,
got a question. How
yeah.
did we come up with negative one?
With negative one. What's it?
Yes.
We got the opposite of positive one, which is negative one, because that's the only way we could write the domain function under this situation here.
Okay.
Yeah. Yeah. So our next question, now we're going to, our next question in this case here is sorry, just give me a second. Okay, so our next question that we are going to look at, the more we solve such questions, the more it's going to easily assimilate inside. Yeah, like how they're solving the question, and you guys are actually going to see the sequence of how it goes and everything else. Yeah, so our next thing, our next question is actually going to be, in this case here, we're given gx is equals to ln of 2 plus ln of 2 plus x.
Wait,
Usual.
Mona, the question.
Yeah.
So when we just find the values of x and we write the domain, so that's the end of the question.
Yes. Yeah. That's the end of the question.
All right.
Yeah. Okay. So our next question is, we've been given gx is equals to ln of 2 plus x, where x is a member of real numbers. As usual, the first thing here we are going to do is we're going to say x is a member of df, right? You bring about your equivalent sign. You're going to get rid of the ln. You only get what's in the brackets, 2 plus x there, as usual, greater or equals to 0. Yeah, sorry. Yeah, greater or equals to 0 as usual. Then from there, we're going to maintain the equivalent sign. The 2 will come this side. We're going to have x. Yeah, the 2 is going to come the other side. We're going to have x going to be greater or equals to -2 in this. We have greater or equals to -2 in this case here. So what happens in this case here, our x here is not squared. And the reason, and one of the other reasons is why in the first question we actually had -1, apart from us getting the opposite of +1, is the fact that what happens when you square root a number. You're always going to have one answer that's positive and another one that's going to be negative. This is why in this case here, our other reason is, this is why here we had negative and positive here, because when you square root both sides here like this, as usual, you always have x is always supposed to give you two values. That's why in this case here, we have our -1 and also have our +1 in the first sequence here. Now in the second sequence here, our x is not squared. It's just x alone. So what happens here? So in this case here, when the 2 went the other side, it became negative. That we all know how that goes about. In this case here, the sign won't change. Why won't the sign change? Because here our x our x there is not, they have a negative sign there. It's just the way it is. The sign will only change when your x or whatever it is that you've been given has a sign that's negative, and you have to get rid of the negative. That's only when the sign changes. That's what happens here. So in this case here, our x is greater or equals to -2. That we found there. Now what's the next thing? Our next thing here is now for us to now write our domain function. Write our domain function. Now in this case here, in this case here, we're looking at an x that is not squared, and it being not squared will give us a possibility of whatever it is of our x not being equals to 0, like at the beginning here, because the x here is not squared. So there's a chance of it not giving us an equivalence of 0. So what happens? So now what happens in the sense that your x is not squared and you may not have an equivalence of 0? That means the only possible sign that is there is it only being greater than 0, and there not being an equivalent sign, because equivalence only comes about when you have both sides which are possible of you to actually have. Like in the first question, you have an equivalence. You have an equivalence there because our x was squared, and our x was squared. And when your x is squared, you have a possibility of having both an answer that's negative and positive. And normally, those two answers which you find can bring about an equivalence. Now, in this case here, there's no equivalence. So what will happen? What will happen here is that we can rewrite this whole thing here by saying we'll have 2 plus x will just be greater than 0, as we are greater than 0 like that there, so that we can just have our x will be greater than our x will be greater than -2. Oops, sorry, let's cancel that. So our x will be greater than -2 in this case here. So what we'll do is we are going to get this side here, and then for this side here, we're just going to cancel it there, because we've seen that no, it can't give us an equivalence. So our equals to sign there shouldn't be there. Like this sign, this equals to here shouldn't be there, because our x here is not squared. This case here is a different scenario from this situation here. This one here gives you a possibility of an equivalence, but then here there's no possibility of an equivalence. Here there's only going to be one possible solution. Here there are 2 possible solutions. That's the difference between this question here and this question here. Yeah. So what happens from there is that now we have our x is greater than -2, isn't it? And then from there, what's going to happen there? We now have to write our domain function like this one here. So in this case here is different from this case here. Like in this case here, our final answer here, we had 2 different answers, isn't it? We had this answer here and this answer here. Here we only have one answer. We only have -2 in this case here. Now, what's our next process here? What's our next step we have to take from there? So what we do is, as usual, you're going to say, we're going to bring it down. We'll say df is equals to. Now, in this case here, it just says our x should be greater than -2. And there's no equals to sign. When there's an equals to sign, at least it gives you a more definite solution. So what you're going to do is you say, okay, since our x here is greater than -2. So this situation here is more open than this situation here, because this situation here has a point that's starting and a point that's ending. This one here just has a point. There's no starting point and there's no ending point. So there's a starting point here, but then there's no ending point. And because there's no equivalence there, so this here does not fully dot down or say that no, we should start from our starting point surely is -2. Here it gives you a more open starting point, and for that reason we are going to have a domain function as your sign. This side here is going to be open. It's going to be open. Have your -2, comma. We don't know, since our x here is positive, isn't it? Positive infinity, open bracket as well. Why? Because look at your sign. Your sign here will sell you out. Will give you a more vivid way of how to write your domain function. In this case here we had a starting point there and ending point there. We had an equivalence there, and we had a more definite way of how to write this. This is why in this case here it was closed, because here this question here is more accurate, more precise, has been made very, very easy. This one here is more open and more generalized compared to this other question here. Is why in this case here we're going to actually have, yeah, it's why in this case here we're actually going to have this situation. We'll have our domain function will be equals to open bracket -2 comma plus positive infinity open bracket as well. So this is our domain function for this one here. This one is for this one here. So we have these two different scenarios. So this is one of the things, yeah. Now, apart from that, now what happens now? Apart from that, remember that there are times. Remember that in this case here, we've been given x is squared here. Our x here is not squared. It has the power of 1. Now, what happens if you've been given a quadratic function? And in that case, remember you have to go back now to how you solve quadratic functions, how will you come about it, and everything else. So you now have that. You now have that possibility, isn't it? So, okay, John, let me just flip this paper. Okay. So now, our other possibility is now that they can give us x to the power 3, isn't it? Yeah. So we're going to just say, remember, this is how an example of a quadratic function of where you have, at times, guys, they can even start from like x to the power 3 plus x to the power 2 or whatever, different scenarios, but this is just your generalized quadratic function if it's like this. And then we all know that I'm sure you guys remember from last time, delta is always going to be equals to b squared minus 4ac. And this comes from your actual equation, which is how's that equation? Negative b, isn't it? Plus or minus square root of b squared minus 4ac, everything over 2a. So normally this part here is equals to delta. This is why it's been given like, this is why they say delta is equals to b squared minus 4ac. Basically, this is just like how it's been simplified. Yeah, so you guys remember this and everything else here. Now we have different scenarios. What happens if your delta is equals to 0? What happens if your delta is equals to 0? If your delta is going to be equals to 0, if your delta is going to be equals to 0, yeah, if your delta is equals to 0, meaning that your y, is going to have the sign of a. Yeah, this is our first scenario. Like if our delta here is going to be equals to 0 and everything else, meaning that our actual value is gonna be a. Like our y is going to give us a sign of a. This is our first scenario. What happens now if your delta is negative or your delta is positive or your delta is what? So if your delta is going to be greater than 0, normally the racine of y is going to give you negative. It's going to give you negative a. And if your delta is negative, meaning that the y is going to have a sign, will give you the y is going to give you a racine of a. So what am I trying to say is that we have this scenario, we can have that scenario there. Have so many different scenarios, and all this can be proved if you find your delta here 0. If you find here it can be greater, what. You can find different values here. Yes. Now what happens from here? What happens from here is now that whenever you're solving such functions, you have different possibilities, different answers you're going to find. It's very, very diverse, very vast, very just different and everything else. Yes. So one of the things you're going to do is, what happens now is that from there, because of you might finding different answers, you've got different possibilities and all of that. So this part here, just trying to remind you that there exists something like this, and this is a simplified formula. This thing comes from this formula here. yeah, this comes from this formula here, and you've got different possibilities that exist, and you should be aware of the possibilities that do exist. So this is for this part here. Yes, yeah. So the next thing we're going to look at, let's go to, let me now go back to the to the PDF. Yeah, let's go back to the PDF now. That's true.
Okay, now we're going to look at the PDF that we've been using. Just let me share the screen. So we've looked at those different, looked at ways of actually writing just the domain function and everything else. Excuse me, right? My microphone on. Okay, perfect, right, it is. So we look at these possibilities. We look at the possibilities of writing, like how to write a domain function, other examples, how to write a domain function and everything else. Yes, yes. So so this part here, it says we have A which is the part of R, and this is an example I was giving you. Then now in our case, our this A was D. Here it's A. It can be D. It can be anything, but normally it's D. Normally it's D because of the DF. It has to be D. It cannot be AF. It has to be DF. Yes, yeah. So in this case, we have A, which is a part of real numbers as usual. Yeah, A is a part of real numbers and everything else. Just like we have did the other one, it's F. They are N real numbers, yeah. And then it says we call A the domain of, yeah, it says we call N the definition, we call A the domain of the definition in function of F, just like the other one. In the case I gave you when I introduced the topic, it was D in this case here. D was our domain, which is more precise because the domain and D over everything else. Yes, yeah. And then from there we know that F exists in different ways. Our F because F can be in function of X and everything else. So whatever value you find can be, it's very different, can be negative, positive, it can be a neutral number, it can be negative, positive, and everything else. This is why in this case here they are talking about it being minore, majore, born, and everything else. It can born means both majore and minore. When you say both it be majore and both minore, you can actually give an example of the first example we actually had, where our domain function had -1 was less, or no, -1 was less. Where our -1 was where our -1 was less or equals to x and less or equals to +1. This is the case here. This case, then the first case we can give an example of the one that we're looking at just now, where our x, where our x was less than, so it was greater than -2. This case here, we haven't yet seen something that's in the case of majority, but at least you guys have seen an example, and you guys actually then see how we are bringing down section and everything else. Yeah. Now the next thing is that let's see. So what happens is at born. Sorry. Yeah. There's something that's called how do I say this? Okay. That's it. Anyway, okay, there's something that can be bigger, or values that can be bigger and values that can be smaller. Now, in the case that your values are both small or your values are both big, in this case here, in this scenario here, the values that you were looking at, the values that they had assumed, caused, or whatever it is, there were values that were actually greater and all that. This is why in this case here, You're looking at it being in this situation here, because this situation here, like the way it's been written here, is very similar to the way it's been written here. To the way it's been written here, actually. The only difference, no, sorry. The way it's been written here, yeah, the way it's been written here, it's very, very similar to the way it's been written here. The only difference in this case here, they have introduced now it being introduced this and everything else here. Otherwise, it's them just introducing these things to you so that they don't seem different and all that, even when you see them and everything else. Yeah. You know, what actually happens is that normally under a domain function, at times your domain function can be in two different possibilities. You can have f and you can have g. I don't know if that has been given here. Okay. I don't know. Okay, it hasn't been. Maybe if we go down, everything else, maybe it's there somewhere and all that. Yes, yeah. But there are times, yes, yeah. But then there are times when your domain function is in two different ways. You have function f and you have function g, and the same thing is going to apply. If you have function f, it's going to be f. It's going to be the g. Yeah, but everything is going to be a member of real numbers, just as always. And normally, what happens now if we're not going to have an equality of the f and the g, that means we're going to now say our f will be equals to the g, and everything else. Yes, yeah. And then from there, if our f is equal to the g, meaning like f of x is going to be equal to g of x. Yeah, as usual, our x is going to be a member of real numbers that we already know here. So we have that situation there. Now, what happens now? What happens now when you've been given an image? Yeah, when you've been given an image of a part, because we know our main situation here, we're looking at our domain function, df, right? Now, what happens now if you have an image that's a? If you have an image that's a. Now, let's now see what happens when image is a. If your image is going to be a, that's going to mean that f of a will be equal to f of x, because your a is coming from your x, because f of a is acting on an image of f of x in that case there. And let's say for example now in f of a there's now a value that's called y, meaning that y will be a member of f of a, right? And then now that f of a is equals to your f of x, because f of a comes from f of x. So from there you now have define, can know that this and x is going to be a member of a, because we know that no, our f of a is an image of f of x. Now in f of a we have a y, and that y is a part of f. Now I have to now redefine everything, because in my analysis you always have to define things and explain why this is this way and everything else. Yes, yeah. So in real functions and real variables, there are times when you have an image of your domain function. And in this case here, the image that we're looking at here is your a, an image a. And in an image a, there is a part that's called y. Now, meaning that y is a member of the a, right? Remember now, the f is a function of a, and a is an image of x. So now let's now look now for those that are lost in what I'm saying and everything else. Yeah. So we're going to give an example. Let's say for example we've got two people. There's Mapalo. Mapalo is the main. We say Mapalo is the main thing. Mapalo is an image. Oh no, we say Mapalo is just Mapalo. Right now, when Mapalo looks into the mirror, Mapalo sees her reflection, right? That means now Mapalo is going to become the domain function. Mapalo is df. When Mapalo looks in the mirror, she sees d. Sorry, she sees dg. Let's suppose dg. Now, when she looks at her image, on her image there's an eye. Like she's got two eyes, two ears, she's a nose, a mouth, and everything else, isn't it? Now let's say now her nose is a part of the image, right? This is now what we're saying, that we have our main thing, which is our x, our X is equal to Mapalo. Mapalo looks into the mirror, he sees an image. The image that she sees is called A. Now on her image, you can see a nose, and that nose we name it as Y. Now, how are we now going to define that? Meaning that Y is a member of X. Meaning her nose is a member of her image. And where is her image coming from? Her main body, which is X. And for this reason, this is why we now have to now define and say that Y is going to be equals to X, meaning that her nose on her image is equals to her body, which is X. Because her body is the object. And without an object, there's going to be no image. And this is why in this case here we've got that scenario there like that. Yeah. So oh, sorry, I just saw someone's question where they said, so should we cancel like that in an exam or you made a mistake? No. Listen, the example where I had given you where I had cancelled them, like I first gave you a generality. So the reason why I cancelled was, first of all, I gave you guys like just like the way we had applied it like in the first situation, like where it was greater or equals to 0, right? In the first example. Now I applied the very first example in the second example. I followed all the steps I had done in the first example. Now I have to now show you guys. So I showed you guys that, so at least you guys can see the steps we had to use. Then now I showed you guys that so that you can now see how it now moves from it being greater or equals to 0 to it just being greater than 0 in that case there, so that you guys can see how we moved from this side here and how come we have, so at someone can come to ask, no more, why did we add greater or equals to 0? How come this time here things are different? That's why I first showed you guys the first thing I had done, and then I explained to you guys why it's not this way and why it's this other way. Yeah. But in an exam, you can't do that. You have to just know that no, it's like this, and you write the way it's supposed to be, and don't start answering things because no. Yes, yeah. So we talked about an image. Yeah. Yeah. So apart from that, so what happens now is that other part is very important. Let's see. Let's just run to the notes. Yeah. The notes are equally very, very important. Yeah. So look at this, let's see. We have other examples here, but then I've solved for you guys an example that's more precise, like and everything else. So we want to look at this example here. It says in a suite. So in this case here, we have A there with different intervals where the brackets are open both sides. This here is typically like the one that we had in example 2. We haven't yet had the example where we have this solution here. Not yet. This one here was like example 1. So guys, you see the possibilities which are there, right? When you find the elementary, you have both brackets open, one bracket open, one bracket closed, open, closed, closed. Yeah. So you have this possibility here. Then now there are times when it can be, if you start with negative infinity, and then you have your answer here and everything else. So we're going to look at times what happens if our first part here is infinity and not the value that we have found in this case. So we haven't look at an example like that here. So you guys can see like how we can have different intervals, very, very different diverse intervals and everything else. So this right here, guys, is a possibility. Okay, so you have that there. Then they're giving you like other possibilities as well here and everything. I'm sure that you guys know what A with the bar means. A with the bar means is basically like the opposite of what you like for A is, let's say for example, our A is equals to -2. Now they say A bar will be equals to +2 because A bar will be the opposite of A. Period. Yes. So that's that. You see, this is why you see what they've done here. They say that we have your A bar there, and it's been put as A because A bar is opposite of A. The same way, same way 2 is the opposite of -2, the exact same thing. I'm sure you guys have done application of a bar when you look at in algebra. Algebra, there's a lot of this, a lot of these things. The best of it, cash. Yeah. You guys also remember that analyze is very important because you're going to apply analyze in so many topics, like even so many other subjects. In physics, you find analyze, in math, you find analyze. So analyze is the baby of Morocco. So, and then we now have next thing is limit of a function. Yes, let me see. I want to give you guys at least something that you may not have be more familiar with, so that we can not spend so much time with the cool, but then so that the actual notes can be left for you guys to read through and everything else and all that. Yeah. Let's see. Okay, so now under limit of a function, so we have different scenarios. You have different scenarios. Let me look for an example. Oh, by the way, I'm sure you guys know like how to know if like when solving limits, like how to know like no from here. I'm going to move to this other. I'm going to move to solving the limit in another way because this is not equals to everything else. I'm sure you guys already know that from our basic mathematics. Be following it because they're going to find these things. I'll give one example. Here's an example on your function. Okay. So guys, what happens at times, they won't give you actually normally they don't really give you such an easy function, like where like the ones we looked at, where it was like 1 plus x squared. At times they can give it like it can be maybe they say they can give you two quadratic functions over each other. And then now you don't have to now find the main function and everything else. Now how are you going to do that? Yeah. So we're going to look at that. That's for the let me find something that's a little bit more. That's going to at least be able to be applicable in all other situations. Okay. All right. Let's try out. Okay. Let me get another example. Let me just stop sharing this too.
All right, so another example. Let me just move from the side. I think it's gonna like this in this room. Okay. Okay. What example am I going to give? Okay. Okay, sure. Let me just stop sharing this. Stop share. Perfect. Okay, so we'll look at an example. Okay, no, yeah, let's see. Which example am I going to give? Okay, let me give you guys this example here. So, okay. Example. Okay. We're going to have h of x is equals to x exponential. Okay, so in this case here, what do we have? We have got two different, in this case here, we've got two different equations, as you guys can see. No, actually, no, they're actually the same equation. No, this one is actually way easier. It's direct. I need something else that's not so direct. I think this thing, that's a very good example. It's the same thing, yeah? Yeah. Okay, well, it's okay. We'll work with the same one. So in this case here, we've got we've been given this question here, right? Then now we have to solve it. Like, I have to now find the domain function and everything else of this question here. How are we going to go about it? So the first thing, as usual, we're going to say x is a member of df, right? Equivalent sign, it's always like this, guys. So what do we have? We're going to say ex minus e negative x. And this here, what happens is that we are going to get, normally get the value that's at the bottom, and the value that's at the bottom, by definition, it cannot be equals to 0. So in this case here, this is how we're going to write it. Just under this situation here is how we're going to write it, because if we say greater or equals to 0, meaning that here already our fraction here is already going to be unsolvable. Yeah, so in this case here, we're going to say it's not equals to 0. And when it's not equals to 0, what happens? We're going to say our equivalent sign, that ex not equals to negative, sorry, e to the power negative x. That we already know there. And then from there, as usual, ln of ex is not going to be equals to ln of e negative x there. Remember, this is like this here is like this, it just be like that. From there, what you're going to do, you just get what you have there. We have x not going to be equals to negative x, like that there. From there, yeah, and then from there, this will come this side. So from there, this is going to come this side there. Then you're going to actually have 2x not equals to 0, because x plus s is going to be equals to 2x. And then from there, when you divide both sides by 2, you have x is not equals to 0, like that there. And from there, this domain function, guys, like this question here is actually like, it's one of those questions that's just solved like this. It's like it's like a rule, I should say. It applies like a rule. So in this case, say if I do it like this, and then from there, you are actually, sorry, it's not df, it's supposed to be dh, sorry, because yeah, then from there, and I'm going to say dh is equals to real numbers, where you have our 0 like that there. Then this whole thing is gonna be equals to real numbers as usual. And this case here, guys, this is a case where it's like it's a special case. It's just solved like this. This is just how it's solved. It be like this. It just be like this. For this one, here's just how it is. Yeah, so it's very important. You have to keep this. You keep this and all that. Yeah, you keep this and all that. So yeah.
But for the
So that's that for this question. Then there are other scenarios where we have
am I not audible?
no, the other ones I'm going to give you guys to solve them. But I'm going to solve one more question. Let me find one more question that I can solve. to just help you guys out. Let's see.
Mono.
No. So guys, remember what I did there? Remember what I did for this one? For this one here, I got the bottom one. It's a bottom one here I'm using. So let's say, for example, here, if it was a different thing, I got the bottom one here so that I can simplify the bottom part here. This is why the bottom part here was not equals to 0. This is the reason why in this case here, when it's a fraction, get the bottom value, and go on the bottom value, and then the bottom value is just going to give you your, it's like the main thing. It's like the main thing. You start from there. But now in this case here, our bottom part and our top part here was the same. Now let's say you've been given two different bottom parts. Two different parts. The first thing, start with your bottom part. Make sure that bottom part is not going to be equals to 0. The way this one here is. Then now, normal. Okay, let's do this. Let's say, for example, I've been given f of x. I've been given f of x is equals to let's say, okay, ln over 2 minus x over 2 plus x. So I've been given this here, right? Now, how am I going to solve this? Say now find the domain function of this here that you've been given. How we do this? Say, okay, no. The first thing we do is, as usual, the bottom part. Well, first thing, normal, as usual, d. So f x is a member of d. Df is going to, as usual, your equivalent sign. From there, what you're going to do here, from here, what you do is the bottom part, as usual, 2 plus x is not equals to 0, right? Have that part here. Now we look at these two. No, okay, so they're different. So okay, so now these two here are very, very different, very diverse. What's our next step? Our next step here, say okay. So when you say and, this and, guys, is very, very important. At times this and can change to o, and you guys know from algebra and then the o what it means there. So from there, what we do is we're going to get the whole fraction now. We'll say 2 minus x over 2 plus x. This will be greater than 0 in this case here. Remember, these guys, look at your x values here. They're not square, they're not what. So just stick to this here. And then from here, we do that. They will know that our x is going to be not equals to negative 2. And we'll just keep this 2 minus x over 2 plus x is greater than 0. You have this here and there, right? So now from here, what happens here? And so now from here, what happens? This actually here is going to give you different possibilities. So like at times, what we do is, since in this case here, we're looking at a fraction, and this is a different case. What we do, like we'll draw some table going on like that there. We'll put our x. How many is we have x? We have x. 1, 2, 3, 4. One. Then we're going to have x minus 2 here. Have 2 plus x, and then now the fraction itself. Oh yeah, fraction itself. So it's 2 minus x over 2 plus x. And now in this case here, what are the possible values? The possible values here are negative infinity. The other possible value here, because we have negative 2 there, we need to write the opposites of these two. So we'll say positive 2 and positive infinity from there, like that here. Yes, yeah. So what's our first thing? Our first thing per usual is going to be, our first thing per usual is actually going to be okay, so that and that there, this and that there. Don't have a positive sign there like that there. Nothing that there, have a positive sign as well there. This, that there, negative. That there, negative. It's going to be negative. No. No positive here. Here it'll be positive there. Here, that there. Negative there, positive there. Because if we here becomes plus there like that, there becomes plus there like that there. Either way is here, and it's going to give us that there. Negative there, that there. This one here does not positive, that there. No, here you have two possible values like that there. And then this negative will become plus, here it can become negative actually there. This one here become plus 2, there, that there's possibility of it being x there, so it being positive there, but it can be negative as well here. But anyway, boom, that case here, that this one here dominates the other one there, so in this case here is negative and all that. Anyway, yes, yeah, so like normally when you be given like a fraction like this, when you're given a fraction like this, hey, have ln of 2 minus x over 2 plus x, the first thing that we do is, as usual, we have to write x is a member of the f. You get your bottom part there, make sure it's equivalent to, it's not equals to 0. You get your whole fraction there and you make it greater than 0. You solve for this part because it's easier. This part here, don't solve for it, just leave it the way it is here, like that there. And then from there, we're now going to draw it. We're now going to make a table. Guys, this table is very important whenever you are solving questions like in this situation here, because in this case here, we are looking at two different things. We have x is not equal to -2, and then we have a whole fraction which is said to be greater than 0. So what happens is you're going to actually write like what you've been, like your possible things, that like what you have. So we have our x, we have x minus 2, which is there, which is our numerator, x plus 2 our denominator, our initial fraction, that there. We have our negative infinity, which is a possibility of it being there, -2. We already have a -2 there. The opposite of the both of them, we have them there. We've applied them here, we've applied them here, and then we have applied them here, and then from here and now from here what happens? From here we now have to like find 1 2 3. Okay, from here we now have to find like a possibility of like of what signs we're going to have in there, and then from there what you do is you're going to get what you've been given as a numerators on top, and then replace them in your initial situations, and then from there you're now able to find the signs and everything else. There are times when your signs can be a particular way. Maybe your signs can be both negative and positive. You're going to put the Kaseko here in the line to just show that it's gonna be like that and everything else. I don't know whether you guys know, you haven't done this already. Yeah. So there's this other possibility here. This table here is important, so at least you know like your possible values here and everything else. So even as you're writing your final domain function, you're not confused. At least you have an open idea of what it might be and everything else. So now we've drawn our table here. What's our next thing? Our next thing here is for us to write our domain function of this whole thing. As usual, the f is going to be equal to, in this case here, our value is -2a. Our value is -2. Our sign for our initial fraction there is going to be greater than 0. So our starting point there is -2. Our starting point there is -2. And in this case here, remember in front is going to be open like that there. Look at our sign. There's no equivalence. Actually, the whole thing here, there's no equivalence here. Now, in this case here, we're going to get our +2 as it being our last value. But then we won't say that no, it will end here. We won't say to end here. No, we're going to leave the other bracket open as well inside here, such because when you look at our table here, has a negative infinity here and positive infinity here. So it's more precise for you to get your actual values, which is -2 and not get your infinities. But then you get your -2 and your +2, and then make an opportunity of there existing your infinity and your infinity that's negative and positive. This is why in this case here, our brackets here are open. They're very so many different questions like this, and such things that actually come in the exam and everything else. So like you really have to solve a lot of questions under these things, so at least you see how they are solved, and you get used to the method and everything else and all that. Yes, so there's that there. Now, another thing here we're going to do, what time is it? It's okay, it's almost 10 a.m. So what we're going to do is, the next thing we're supposed to do from here is a couple of notes. We have a lot of notes to look at and everything else. So what I'll do is, right now I'm going to give you guys an exercise. When we come at 15, even though your friends are not here, I know people are still asleep, and that's very much okay. People are still asleep. This is why I'm sure we're beating this class and everything else. Yes, yeah. So what we're going to do is that we're going to I'll give you guys a quick exercise that you guys are going to start doing. Yeah, you guys are going to start doing according to what we've been given here. Then you should, guys, I want the answers. I want your answers. This class is going to end when I give you guys the exercise. I'm even giving you guys an extra 30 minutes to start with the work, and you do it. Yes, yeah. So I'll give you guys a quick exercise, and I'll also give you guys work on limits as well, because I'm sure you guys know how to solve limits. Right now I'm writing the exercise, so like right now I'm writing it right now. So I'll give you guys the questions right about now, so that you guys can solve. You tell your friends, guys, what time is it? Right now it's 10. Before 14:30, you guys, you send the answers. It's a very simple exercise. It's not even hard. Very, very simple. It's very simple. So, very, very simple. So number one. No. I don't know. Does anyone have a question as I'm writing this work? Please ask your questions.
Yeah, I have a
If you have a question. Anyone with a question? There are no questions?
No.
No questions?
I'm
You may have slept in this class. I'm sure all of you guys are just asleep.
Can you get me?
Sorry. Wait, hold on. Okay. Chill, sorry. Damn. Yeah, you're saying? I can get you.
Wait, can you please upload the video before 15 hours? Like, we didn't have power here in Sal.
Oh my gosh, you never had power. Okay,
Yeah.
I'll tell that. Okay, I'll tell Melissa to do that. I'll tell him to do that. Yeah. I'll tell him.
Okay. All right.
All right. Any other questions, please, before?
I've got a question on the signs, like the table. How are we finding all these signs?
Or the signs?
Yes.
Signs. So what? You have one side where you have like equations. We had 2 minus x, 2 plus x. We had a whole fraction, 2 minus x over 2 plus x. And then on the other side, we had different values. We had negative infinity, -2, +2, and positive infinity. So what happens is you replace your values in the equation, and then that's going to help you find your answer. Sorry, your sign. Yeah, that's how you find the signs. Yeah. Wait, I hope I did explain that, I hope I don't know whether I explained it well enough, but that's how you find the signs. This is I2. Guys, it's very simple, this exercise. It's just application of what we've done, It's very, very simple. There's nothing hard about it. You guys can do this. People are very smart. See how far you've come. Madam. Yeah, let's see this one here. Which other one? Yeah, the streets. Guys, any other question? Please ask your questions. If you have questions, even under sweets, name it, ask your questions.
I've got a question on the same table that we were from solving.
Okay, ask, please, go ahead.
There was that column that had +2 and infinity in the same column. That one. When we didn't split them apart, so were we replacing the values simultaneously in the equation, or what? How are we going about to finding the signs in that column?
In that column, one of the ways you can do it actually is by you just replace them like at the same. Maybe let's say you can start with, because let's say for example in this case here, like the first one where you have 2 minus x, you can't replace both 2 and infinity at the same time, because there's only one value of x. So you first start with the first one. What happened? We first start with the first one. When you replace the, like here, 2 minus x, and you have 2. What is x? You put 2. The value, like the sign, yeah, like this. So what happens is the first sign there is here is going to become 2 minus 2. It will give you 0. You will say, okay, so there's not much possibility, eh? So the other one there is now infinity. You place the infinity there, and there you already know, okay, no, it's going to be negative there. You put a negative sign there. Then you have the other one there where it's 2 plus x. Where there's x, you place 2. You place 2. 2 plus 2 is 4. Your sign there is already positive. When you put positive infinity there, you still get a positive charge. So a charge, positive sign. So you have a sign there. Now you have your other one there where the first case here is you have got your 2. So where is the whole fraction, 2 minus x over 2 plus x. Where is x, the first one we're going to replace with 2. Your numerator is going to give you 0. Your denominator is going to give you 4. You're like, okay, the answer is actually going to give us 0, and 0 is neutral. Then the other possibility is on top there, you replace with infinity. On top there, your infinity is going to be negative. At the bottom is going to be positive. Your answer, you find your sign there, negative. Then now the other one there where we now have negative 2. Negative 2, you replace where the first one, 2 minus x. Where is x put negative 2? When you negative signs, when they are multiplied, what should finna do? It's going to turn into positive. You have your plus there. You're going to have your plus there. And then for the other one there, it was supposed to be negative there, where you got 2 plus x. They have negative 2. When you place there, the sign you're going to have there is negative, not positive. Oh no, sorry. For this one here, it becomes 2 plus x, right? Yeah, it becomes 2 plus x. And then in this case here, when you replace your x with negative 2, you're going to actually have 0. And 0 is neutral. And for that case, bam, you got positive. Oh, period. Now the other one, you got 2 minus x over 2 plus x. Where there's your x, you replace with negative 2. The first part there, you're going to have 0. Then the bottom part there, you are going to have 4. 0 over 4 to give you 0. 0 is neutral, positive. That's all. And now infinity, negative infinity. Where there's negative x, negative infinity, there you change to plus. There you change to plus. Where it's plus x, they are usual. Negative signs always dominate a positive sign, so you're going to have negative there in the box there. I'm looking at the first box with the signs. The other one there is going to be negative. So 2 minus x over 2 plus x. So you're going to replace negative x at the on the top there. It will stay positive. Down there it will be negative. Remember, negative always dominates negative sign. This is now how we found all the signs in the table. Have you understood? Or I should re-explain it and show you guys the table again.
Oh, I've understood, but I've got another question.
Sure.
This time not on the table, but on that question where we had about the e's, the e power whatever and the like.
The what?
The e power x.
Okay.
Do you remember that? Yes.
Oh, sure.
Yeah, as in there was a part where we reached that e to the power x is equal to e to the power negative x.
Oh no, it wasn't equal. It's not equal. It was not equal.
Not equal to. Sorry, e to the power x not equal to e to the power negative x.
Mm-hmm.
Now, my question is, wouldn't we have solved that question without introducing the ln?
No.
Couldn't we have solved that question? As in, is it just a mandate? Is it just a mandate that we just need to add in the logarithm, or isn't it possible that you can also have solved? We could have solved that question without introducing the ln.
No, you have to solve that question by introducing the ln in that case, because you don't even know what your value of x what your value of the x there is. And normally remember, like whenever I'm solving exponentials and ln, like normally those two, they go hand in hand. Let's say for example you're trying to get rid of the exponential. How would you get rid of the exponential? You have to introduce the ln, isn't it?
Yeah, that's why my point is, like, they are of the same base. So I thought maybe because of the same base, we can just equate the x to each other, and then we find the value of x.
Indeed, okay, like in this case here, unless if we didn't add the ln, unless we knew the values of the two, it would have made it easier for us to just solve, because we would know like what the power is. But then in this case here, we don't know what the power is. It's just x, and x can be any value. So we still have to show that we are trying to simplify the work, because if we didn't introduce the ln, how would they know that no, we're trying to simplify the work? In this case, like in the case where you don't add the ln, is when like you already know like what your value of x is, because everything has already been simplified. But then in the case here where things are not simplified, and it's now you to actually show that no, I was actually trying to simplify this work here. This is why in this case you had to now bring about the ln. Yeah, you've understood?
Yeah.
Okay, any more questions? Any more questions? Anybody with a question?
I really can't see the exercise that you are writing down because you're not sharing.
Oh yes, yeah, I'm not. Oh yeah, sorry. Just hold on. I wanted to just write it down quickly, because if I start holding my phone up in the air, I don't know. I want to be able to write fast. Sure, I'm about to send the work. Just chill. Just hold on. Give me a second there. I'm almost done. There are only. The sun. I guess I've been there. Okay, I'm almost done. Let's see. Let's see other question. Have you guys already said solving limits with Ernest? Has he given you any limits? Huh?
Yeah, we had solved it the previous time, although he has not. Some of us had really terrible network, and the recording was not done. Plus, Ines also didn't send the work that he did, so we're still lagging behind on the previous work. Some of us on the previous work that we did.
Okay. Okay. Anyway, okay. I'll solve one question for you guys under limits, just to give you guys an idea. All right. So the exercise is done, but for the meantime, let me just solve for you guys limits. Need a tiny space. Okay. All right. Let me share my screen. Let's see. Example 3. Okay, perfect. Okay, so example 3. I'm solving the question under limits. So let's say we've got limits of x is approaching 0, and then we've got 1 minus exponential to the power x and 1 minus okay, 1 minus cos x, and then everything is everything is over x to the power 3 plus x to the power 4, right? So that's, I know, can you guys see the question there? Huh? Can you guys see the question?
Oui.
Okay, perfect then. All right, so the first thing here is we've been given this limit here. What are we supposed to do? What is our actual goal? Our actual goal in this case here is for us to find the limit, right? It's for us to find the limit. So what happens is, in this case here, we're going to just do direct substitution. Where there is your x, you're going to put 0, right? We're going to put 0. So, and if you put 0, our answer here is going to be 0 over 0. Going to be 0 over 0, and it cannot be 0 over 0. Yes, yeah. So what actually happens here, because I'm sure you guys know that when you put zero here, it's going to become 1 minus 1. It's going to give us 0. Here, the same thing as well. The answer here is 0. 0 to the power 3, 0 plus 0. And the answer can never be 0 over 0. This here is wrong. So what we're going to do is here, now have to find a way to solve this question. Now have to find a way to solve this question here. So normally, like guys, what happens is that there's this topic that we're going to look at. That's called development limit, whereby your 1 minus x squared is equals to, where 1 minus x squared is equals to x. Sorry, when it's plus, it's equals to x. Yeah. So let's say, for example, what happens is that, like, you are given this table where you have, like, where you've got different values, where your cos x can be equals to something and everything else and all that. So now in this case here, and development limit is one of the easiest ways for you to actually calculate something, because what actually happens, one of the things you should know is that, one of the things you should know is that 1 minus cos x, this, guys, is actually equals to x squared over 2. This is one of the things you should just know. It's x squared over 2. You should just know this. This is just how it's equals to. These are like rules. Then the other one that you should know is x squared minus 1 is equals to x. You should know these two. So we know that this, how we knew this is through another topic, the next topic that we're going to look at. Yeah, which actually helps us actually solve questions, because let's say, for example, if you already know what this value here means and what this value here means, all you have to do is just replace those values with your actual values. So here we're going to solve this question by the use of a development limit. So what we're going to do is we're going to say, so since we can't just write that, no, it's equals to what, how will the professor know what you've done? So here we're going to say, going to write this. Sorry. Sorry. Okay. By development limit. Development limit. Okay. So, oh, sorry. Okay. So I'm going to write this. So since here, okay, what we've been given here is e to the power x minus 1 is equals to x, right? And then it says 1 minus cos x is equals to x squared over 2. But then now in this case here, look at, in this case here, it's 1 minus ex, right? And here it's ex minus 1. And if we write this like this, it's actually going to be, it's going to be negative ex plus 1. You guys, you've seen that, right? So what happens is these ones are equally the same, but then this one here is negative. So in this case, what's going to happen is that our value, this value here is going to be equals to negative x, because our initial value is like positive x. So like that's how it's gonna be, you know. So what actually going to happen is, so we're going to now bring down the limit. So we'll bring down the limit. We know what this value is equals to. It's going to be equals to going to be equals to negative x, right? We know what 1 minus cos x is equals to. Now that one is going, it's times 1 minus cos x is equals to, it's x squared over 2, right? Everything over x squared plus x to the power, so x to the power 3 plus x over 4, right? And then from here, what's the next thing we have to do? We have to now we now have to simplify this equation here. How do we do that? We're now going to divide the entire equation by x. Yeah. Yeah, we now have to simplify this equation here. We can divide by x, because if we remove one x, we're going to have -1 there, and then from there we're going to have 1 over x. Yeah, okay. So we now have to simplify this equation here by just simple substitution and everything else like that there. And then we are actually going to, yeah. So when we simplify this whole thing here like that, simplify that part there, this, that there, this, and there, and everything else here, we're going to have -x there, because actually is we get rid of the 2. So we get rid of the 2 there. Okay, let's say we get rid of the 1 over 2, right? Get rid of the 1 over 2 like that there. So let me do this. Yeah, there's no space here, sure. So what we've been given there is -x times x squared over 2, right? Everything over x to the power 3 plus x to the power 4, right? Then now here we say, no, let's simplify this. Let's get rid of the 1 over 2. So there we say 1 over 2 there. We simplify that by 1 over 2 there, like that there. So let's see, if we just merge, if we merge all this together, this part here is the same thing as -x to the power 3 everything over 2, isn't it, right? So if we get rid of the x there, what do we have here? We have -x to the power 3 right there. And then now whatever you do on top should be done at the bottom part here. This part here is actually this one, sorry, this half here will change. It's going to change like the position to become 2 over x to the power 3 plus x there to the power 4, like that there, right? Isn't it? Yeah, like that there, and everything else and all that. Yeah. So you've already gotten rid of that. When you simplify this part and this part here, you're actually going to be left with -x to the power 3 over 2 x to the power 3 plus x to the power 4 there, like that there, isn't it? Yeah. And then from there, what you're going to do from here, what we're going to do is we're going to just substitute. We're going to get the x to the power 3 over -1. We'll make this x, we just remove that x there, like that. Then there, if we remove that, if you remove the x squared there, like that there, we'll just say x to the power 3. We're going to have 2 there, 1 plus, if we move that there, 1 plus x, actually this and this is going to cancel, this and this had to cancel there, like that there. We're going to have -1 everything over. If we distribute that there, we're actually going, oh yes, yeah, that there. Then we have 2 1 plus x there, like that, and everything else. Yeah. And then yeah. Yes, yeah, yeah. So when we're going to have 2 there, like that there, equals to, then I remember that our limit is, so we have this, remember our limit is approaching 0, isn't it, right? So where there's x, we're going to put 0, so we're going to have -1 over 2, 1 plus 0 there, which is actually going to give us -1 over 2 as your final answer. Yes. You guys get it, or should I re-explain? Hello?
Re-explain.
Okay.
I couldn't see what you're writing, so re-explain.
Okay, so we have this equation here, right? We're given limits of x is approaching 0, right? Where 1 minus exponential x times 1 minus cos x over x to the power 3 plus x to the power 4, isn't it, right? So normally limits, you have to just substitute your x by what you've been given. So what you're actually going to do here is that we're going to replace our x with 0. So where there's x, like this first equation here, we're going to put 0, and what we find is 0 over 0, and that can't be an answer. That means we now have to find another way of us to solve this equation. The different ways, you can solve by fraction, by what? Okay, yeah, you can solve differently by finding just solve differently. So what we chose here to solve, we chose to use is a method called development limit, where where our fractions have already been given what they're equals to. Now in this case here, 1 minus cos x is equals to x squared over 2 is equals to this part here, right? Then now the other thing we know is that exponential x minus 1 is equals to x. Now in our question, in our actual question there, everything was negative. like the sign that was negative and not positive, they mean that if e to the power x minus 1 was equals to x, the opposite of that e to the power negative 1 is 1 minus e to the power x, right? Meaning that in this case here, answer there is going to, like our x, there's going to be negative x. So the next step we do is we are now going to replace this equation here by what it's equals to, by it being equals to x to the power 2 over 2, and by it being equals to x itself here, right? Yeah. So now the new yeah. So when we replace, so now when we replace, our new limit is going to look like this. It's going to be limit as x is approaching 0. We're going to have negative x. So we're going to have negative x times x squared over 2, everything over x to the power 3 plus x to the power 4. So once we replace 1 minus e to the power x and 1 minus cos x with 1 minus e to the power x is equals to our negative x, we put our negative x. Remember, these two equations here are being multiplied, right? So, and then from here, it's now going to become x to the power 2 over 2. We're going to keep the bottom, our denominator here, which is x to the power 3 plus x to the power 4, isn't it? So this is now how our equation looks like. And then from there, the next thing we're going to do, the first step we're going to do is, or rather, next step we're going to do is, we are now going to get rid of this 1 over 2 the fraction. So what happens is, when you get rid of the 1 over 2, which we've done here, we got rid of it, we're going to be left with negative x to the power 3. Remember, how we actually got this is that when you multiply negative x by x squared over 2, we're going to actually get negative x to the power 3 over 2. So this is actually what you get when you multiply this, and these are the same thing. So what are we doing? We're trying to get rid of the 1 over x. So 1 over 2, so you can simplify the whole thing. So whatever you do on top should be done at the bottom. So here we simplified by 1 over x, and you know that when 1 over x goes at the bottom, like the sign changes, like the positions are going to change. In this case here, you have 1 over 2. At the bottom part here is going to be 2, and in this oh yes, it's going to be 2. Yeah, it's going to be 2 in this case here. Yeah. So as we have actually simplified this other equation here, what we are left with, what we're actually going to be left with here is going to become negative x to the power 3 over 2, x to the power 3 plus x to the power 4 there. And then from there, what you're going to do is you're now going to you're now going to simplify this. We're going to remove our x to the power 3, because 3 is the second highest power, and x to the power 3 is like in each of the, each of the, yeah. So we get the x to the power 3, it's here. When you remove it from there, you're left with negative 1. In this case here, going to be left with 2 open bracket 1 plus x, which is also going to be 2 plus 2x in this case here. And then remember that our limit is limit where x is approaching 0. So where there's x, you're going to put 0, and then 2 plus 0 is actually going to give us 2. So our final answer is actually going to give us negative 1 over 2. Yeah, this is how you found the answer. So the different ways of us solving limits. Yeah, that's one of the ways you can solve limits and all that. Yeah, yeah. So
Sorry,
that's
I
that.
still have a question.
Huh?
I still have a question on the how we got rid of the negative. Is it the half? The half, yeah, there. Yes, because if you can zoom on the paper. Yes, there is the half that that we factor out, and then since you're saying that the same thing we also do, the same thing that we do in the numerator we do also in the denominator. Is it?
Yeah.
So that means we're also going to have, is that a 2 that we have down there, like the opposite of the half?
That's it.
Now,
You have. Okay, look at. what initially happens is that when you remove the half, right? When you remove the half from from the top part, when you remove the half, once the half goes to the bottom, once the half goes to the bottom part, it's just like, let's see, how will I do this? Let's see. Okay, so you have your half there, which was in your initial equation, right? It was x squared over 2. And then when we did everything, became negative, became x to the power 3 over 2. So what happens is we're trying to get rid of the half from the numerator so that we can simplify everything. And if you want, yes. So now if you want, what you can actually do is you can actually just leave the half in this situation here, and then maybe just say, no, what I'm going to use here is I'll use here to make my work easier, I'm going to get my x to the power 3, whatever it is. But then for me I chose to first get rid of my fraction on top so I can make things easier for myself. So what happened is that when I got rid of the half on top, when I got rid of the half on the top part there, what happens is when that half comes the bottom part there, the sign will change. It stops being a fraction, it now becomes a whole number. Yes, yeah. So yeah, that's how the two they came at the bottom there. Yeah, I don't know whether I've explained.
Yes.
Okay. Yeah, so when the half comes at the bottom, it changes from it being a fraction to now it being a whole number. Yes, so that's that, and that's how I found my answer there. But then this can be solved in different ways. If you want, don't get rid of the fraction base. You can first get rid of your x values, because x values there are the ones which are actually common there. So let's say, for example, like there.
Put proper your camera.
Oh, sorry. Yeah, so if you want, you can get rid of the x face and not get rid of the half. So it depends with what you're comfortable with and what you first want to actually get rid of in the first place. But this is just one of the simplest ways to actually solve limits is just by using develop more limit. Yeah, let me send you guys the work. And yeah, because time has already gone. It's now 11. It's past my time. Well, it's almost 11 here. Let me send you guys the work and send you guys this solution here and all that. Yeah, otherwise, guys, don't forget to actually attempt to do the work. Just try and do the work, like the limits to just try and solve the limits. Yes, yeah, you can use any method you want to use to find the answer. Any method is going to be accepted. You don't have to use this method here because there are many methods you can actually use to actually solve limits. This is just one of those. I just chose to solve it like this because it's just easier like this. Yeah, so let me send you guys the question and send you guys the pictures of what we've done today and all that. Yeah. What am I off? Ish. Okay.